Here's a tale that talks about old papers, photoredox catalysis, crime scene investigation, and making a drug candidate with nickel and light. How are these things possibly related? Pull up a chair and find out. Scientific results don't really have an expiration date. If the experiment is well described and the data is reliable, the result is useful for anyone wanting to work in that related area. That being said, it seems the shelf life of scientific papers has been studied a great deal. For this, one can look at mean citation ages, a measure of how old papers are that are influencing new research. Across all disciplines, the mean citation age is about 10 years. One paper on this is by Lin Zhang and Wolfgang Glanzel in Scientometrics in 2017. Among the hard sciences, chemistry is on the shorter side at about 10 years. Physics and biology are somewhat longer at 12 and 13. Mathematics, maybe unsurprisingly, is the longest at 15 years for the mean citation age. On the short side are anything to do with medicine, which seems to be in the 9 to 10 range. One problem that folks can have is that they begin to think papers older than some threshold are no longer useful. But if you know the older literature, you often know the basis for much of the science being done today. One older study I cover when I teach organometallic chemistry is by the well-known chemist J. Kochi and was published in 1979. When discussing common palladium coupling reactions, we tend to draw palladium-0, palladium-2 catalytic cycles. Here is a possible mechanism for a Suzuki coupling, a palladium-catalyzed process where the cycle begins at 12 o'clock with the metal in a zero formal oxidation state, and then goes through several steps as palladium-2 before it returns to the formally zero starting oxidation state. Palladium is one of the rarer elements on Earth, so naturally people have examined the element right above it, nickel, which is far more abundant as a possible replacement. Nickel will do various coupling reactions as well, but it behaves differently than palladium. If you examine the reactivity of nickel aryl bromide bisphosphine, you will find that it is stable under some commonly used catalytic reaction conditions. In other words, direct reductive elimination of aryl bromide is too slow to be involved in many of these catalyses. Kochi found that the oxidative addition involved the initial loss of phosphine followed by electron transfer to form a nickel-1 aryl halide anion radical salt, or tight ion pair. The salt can then couple to give the nickel-2 aryl halide complex, or depending on concentration, the aryl halide anion radical can diffuse away to decompose, leaving the reactive nickel-1 cation. The rate law was found to be first order in nickel triphosphine complex and first order in aryl halide, where the observed rate law does have an inverse term in phosphine concentration, which slows the reaction. Kochi's work suggested that oxidative addition and reductive elimination in nickel-1, nickel-3 cycles were potentially much more facile. Why is this important today? Let's fast forward to a study by Miyake and coworkers in 2018. They found that amines and aryl halide could be coupled to form CN bonds in the presence of nickel-2 bromide and 365 nanometer light, which is in the UV, maybe with a violet tinge. Think of black lights, like they might use at a cop show to see blood. But you don't need luminol with 365 light. Blow is the detection of blood serum on different surfaces with white light, 395 nanometer light, and 365 nanometer light from a paper by Kelly Kears in the Journal of Forensic Science. It's obvious that high-energy 365 light is leading to additional excitation. The compounds you're exciting don't even need to have a color to the naked eye in order to be excited by that wavelength, so it seems pretty natural that it would be superior for forensic applications. However, this may be overkill for your chemistry. You don't really want to excite everything in the reaction, which may cause side reactions and lower yields. Ideally, you want to excite the thing that has to be excited, maybe just the catalyst and nothing else. You can just buy these flashlights from Amazon and other sources, and it's a pretty high energy light, so you may not want to look at it directly and definitely not for very long. Garrett Miyake and company found that excitation gets you to a nickel-1, nickel-3 cycle, or they actually proposed a nickel-1, 2, 3 cycle. This is an example from their paper where the product is made in 91% isolated yield, which is some beautiful chemistry. In related work, Dave McMillan's group published a related photoredox reaction using iridium catalysis to reduce the nickel. Through an indirect process that involves more detail than we need here, the iridium excited state reduces the nickel-2 to nickel-1. While the scheme just shows L for some of the ligands on nickel, there is the substrate amine, quinoculidine base, and solvent donors in solution, all of which could act as ligands. so interpret the L broadly as some donor ligand. We'll also start off with nickel dichloride with at least one of the amine substituents. This gets reduced to nickel 1 by the iridium photoredox catalyst in its excited state, which perhaps gets you to the fast catalysis a la Kochi's favorite oxidation state. The nickel 1 will oxidatively add an aryl bromide to give nickel 3. HBr is lost to base in the solution quinacridine, and the nickel 3 amide aryl complex undergoes reductive elimination to form the product. Note that nickel 1 is regenerated in the catalytic cycle without the need for further intervention by light and iridium, so the metal is ready to do the cycle again. In other words, the reaction is catalytic in photons, and the Macmillan group found the quantum yield to be higher than 1. The above quickly summarizes some beautiful chemistry over several papers as context for a recent paper out of our group on nickel photocoupling reactions. In our case, we were interested in preparation of a specific molecule dubbed ZH71 because it was first prepared by Jolin Hao, who now works at Odyssey Therapeutics. Hopefully, someday we can do a video on the biology of this and related compounds, but it's a little off topic for today. We usually put together ZH71 with a final step involving palladium catalysis, a Buchwald-Hartwig coupling, and we wondered if we could use nickel photocatalysis instead. Our lab has a 427 nanometer lamp that we use routinely, so slightly higher energy than the one used by Macmillan and co-workers at 450, and lower in energy than the one used by Miyake and co-workers at 365 UV light. The general reaction we'll discuss here was developed by Sazia Sultana, Ryan Eleveld, and Matiar Rahman, and looks like this, where we take an aryl bromide or iodide with a primary or secondary amine and couple them with nickel bromide and 427 nanometer light with a Dabco base. The solvent for the reaction sometimes made a huge difference, and there were reactions that worked well in either DMSO or DMA, and there were reactions that would only work in one of those solvents or the other. Here is the UV-Vis absorption spectrum of the reaction mixture in DMA before irradiation and after 3 or 6 hours of irradiation. Also shown is the emission of the lamp we are using. The only thing absorbing in the visible is the nickel-2 complex, which has 2 bands. One that is almost coincident with our lamp at 395 nanometers and another lower energy peak at around 690 nanometers. Here's the spectrum of hexaquo nickel-2, which has 3 bands. Note the 2 different x-axes. The spectrum is from a chapter on inorganic spectroscopy. It is pretty common for spectroscopists to plot their spectra in wave numbers, inverse centimeters, because it is proportional to energy. Other chemists will often plot their spectra in wavelength, nanometers, which is at the top. The 2 scales are inversely proportional, so the spectrum is inverted horizontally from our absorption spectrum of our reaction mixture. Notice that if you look at the axis at the top, there is a peak below 400 nanometers and a little higher than 700 nanometers, just like our reaction spectrum that has nickel-2 with different ligands. The third band in hexaquo nickel-2 is at much lower energy, around 1200 to 1300 nanometers, which is beyond where we scanned our reaction mixture into the near IR. You actually need a different detector with this region. The ground state crystal field diagram for nickel-2 is shown with a spectrum. Nickel is in group 10, so nickel-2 is D8. The 8 electrons fill the T2G orbitals and half fill the antibonding EG set. The big questions are, what is this band at about 400 nanometers that we are exciting into, and what reactivity might it lead to? The first place you usually turn to answer questions like this are to Tanabe-Sagano diagrams. The diagram for D8 complex looks like this, where the dashed lines indicate spin forbidden transitions and solid lines indicate spin allowed transitions. The ground state, always shown as the x-axis in these diagrams, due to the T2G6 EG2 configuration, is triplet A2G, so only other triplet transitions are spin allowed. The TS diagram suggests there should be 3 bands. The low energy band in the near IR is excitation from triplet A2G to triplet T2G. The 2 higher energy bands, shown in our spectrum of the reaction mixture, are excitation from triplet A2G to 2 different triplet T1G bands. Those 2 bands of the same symmetry and relatively close in energy can mix. One of those 2 bands is a literal 2-electron excitation to fully occupy the antibonding orbitals and give T2G4 EG4 configuration. This will make loss of a ligand much more facile and is perhaps what leads to the metal reduction. There could also be mixing of a ligand-to-metal charge transfer, which would increase the intensity of the band and lead to bromide loss to give nickel 1. We propose that by tuning into this band, whatever its character, we are accessing the nickel-1 species without a photoredox catalyst and with lower energy light than used by the Miyake group. This could give the same reaction mechanism, more or less, as proposed by the McMillan group. We could have quantum yields greater than 1, but we haven't confirmed that. Nevertheless, we get good conversion with relatively high solution concentration. After establishing a catalytic reaction works, we'll often pick a pair of substrates and try to optimize them for a high yield under reasonable conditions. What is reasonable depends on the situation, but I'll generally happily wait a day or two for a reaction to give me quantitative yield if required. We decided to optimize this simple reaction of pyrrolidine and p-tolulyl bromide as a first pass to get some good conditions for the reaction. We have a couple of videos on reaction optimization that I'll put in the show notes. One video is really just a why do you do it this way explainer, and the other is a discussion of a specific case in some detail. I haven't really done a video going into the details on the method, mostly because I don't think there would be a ton of interest, but if I'm wrong about that, please feel free to say so in the comments. The short version is that we found that only 3 variables might be contributing: catalyst loading, the ratio of amine to aryl halide, and the irradiation time. The values investigated are tabulated here. We used a full factorial design which changes all of these variables in a systematic way. We also added center points and axial points to get the curvature. Fitting the data gives this model. The catalyst loading turns out not to greatly affect the yield and was left at the lowest value. The variables that do affect the yield are the ratio of amine to aryl halide, reaction time, and cross product of the two, and a second order term in time. The model can be visualized as this curve where x equals ratio, y equals time, and z equals yield. The second order term in time indicates that the reaction can be run too long as well as not long enough. Otherwise, increasing x and modest y will give you optimal yield. Using 5 equivalents of pyrrolidine with 1 equivalent of p-tolulyl bromide and 5 mol% of nickel bromide for 30 hours is predicted to give 100% yield by the model. We obtain 99% yield by NMR and an 82% isolated yield with those conditions. In the course of running about 30 reactions for substrate scope, we found that some reactions worked well in DMSO and did not go at all in DMA, while others went well in DMA and not at all in DMSO. Most reactions worked fine in either solvent. It seems that DMA may be important for encouraging some step in the catalytic cycle in some cases, while maybe DMSO encourages another. The reaction we were working towards to prepare ZH71 is with this 2-bromopyridine, which we prepared using this route we published previously. If you try this reaction with either solvent, DMSO or DMA, you get very little reaction, and ZH71 is barely observable. We backed up a bit and looked at these substrates with coupling partners that seem better behaved. We're interested in this bromide, so we explored its coupling with a reliable substrate that seems to work with most coupling partners, pyrrolidine. We found that we get good yield for the bromide coupling partner of interest and pyrrolidine when the reaction was run in DMA, and only a trace of the product in DMSO. The other coupling partner is 2-amino-5-methylpyridine, and we tried reaction of this with the reliable substrate 4-trifluoromethylbromobenzene. This reaction works well in DMSO and terribly in DMA. In other words, these substrates work best in different solvents. We were prepared to start doing a large trial and error, searching for solvents, but first we tried something I actually didn't think would work. We tried the mixture of solvents. However, it does. We were able to get 57% isolated yield using the chemistry, which is similar to the more traditional palladium coupling. The isolation was unfortunately kind of difficult, so this hasn't replaced our previous method, but it is a promising lead on a new methodology to these compounds. And we learned something about the coupling, especially on the solvent side. Hopefully you enjoyed this brief glimpse into this paper by Sazia, Ryan, and Matiar from our group and their exploration of nickel photocoupling. Thanks for watching. We make these videos for fun and to give back to the community. Please subscribe and give us a thumbs up, and take a look at the rest of our playlist, which has videos at a variety of levels. Hit notifications so you don't miss anything, because we drop vids only occasionally. Thank you.